Swayam Prabha. Digital India. Educated India.
Okay, so welcome again to this new lecture of Fundamentals and Applications of Dielectric Ceramics. So, we will just briefly recap the previous lecture. So, in the previous lecture we learnt about effect of impurities, whether impurities can be intentional, they could be unintentional on the defect chemistry of oxides. So, when you have an oxide MO, when you put in M2O3 in it, then something else, then you bring in extra oxygen into the system. So, this extra oxygen coming into the system will give rise to what we call as electrons, or it can also give rise to metal vacancies. And if you bring in oxide which is M2O, then it does the opposite. So, you can also use these impurities to tailor the defect chemistry. So, suppose some oxide is to begin with oxygen deficient or metal deficient and it has electronic charges, then you can control the defect chemistry by bringing in appropriate dopant or impurity atom to control the defect chemistry. And this is something which is very prevalent in oxide dielectrics. And then second thing that we looked at was equilibrium concentration of defects. So, we just took a very basic thermodynamic route of to calculate the impurity concentration. So, we just looked at the change in the free energy when you consider vacancies and the host atoms as two different entities, and just depending upon the configurational entropy and the enthalpy, balance of between two things will give rise to changes in the free energy. And then if you have a equilibrium concentration at a certain temperature, which means the free energy must be minimum at that concentration. So, we just took the took the derivative of free energy as a function of composition, made it equal to 0, and we got the equilibrium concentration, which is, so your n by n could be equal to exponential of minus of delta HF divided by KT. So, this delta HF is basically enthalpy of vacancy formation, and this could be in EV per atom, or it could be also in joule per mole, and so on and so forth. You can write this as delta HF divided by KT, or it can also be written as delta HF divided by RT, but then you will have to adjust the units accordingly. K is the Boltzmann constant, R is the gas constant. And you can see from this that as the temperature increases, the number of vacancies. So, in this case it would be 2 kT, I am sorry, because you are dealing with pair of defects. So, as a result it becomes 2 kT, but in case of metallic systems it will be just 1 kT. So, whether it is so this N could be equal to Ni is equal to Nv for Frenkel defects, and for Schottky it could be Nvm, and this could be Nvx, okay, because cation and anion vacancies are. So, this is for MO or Mx, but if it is M2O3, then equality will change accordingly, okay. So, you will have to do that analysis again. So, this is basically for binary oxide or ceramic, but if you do the analysis for something like M2O3, then it would be different. If you do it for M2O5, it would be different. The denominator will not remain same, because the number of vacancies that you create as a result of defect formation will be different for every cation vacancy or cation interstitial. So, what we will do is that we will look at the defect chemistry in two systems. One is the stoichiometric oxides. So, now we will look at the defect equilibrium. So, we have seen how the defects form. Now, we will look at defect equilibrium as a function of temperature and partial pressure in these two type of systems. So, when you consider the defects, there are two kinds of defects we can say. intrinsic and extrinsic defects. So, here we can say that intrinsic defects are those. So, what are intrinsic defects? The intrinsic defects are the ones which are basically temperature dependent. And which form in the solid intrinsically. There is no external variable such as oxygen efficiency, oxygen deficiency, oxygen excess or impurity or whatever. So, basically it is a temperature dependent. So, defects like Schottky disorder, Frenkel disorder, these are all intrinsic defects. They do not change the stoichiometry of the system and they can be determined from the intrinsic defect equation. And then we have extrinsic defects. And these defects are created as a means of, so they are caused by, you can say, external factor. And what could this external factor be? It could be impurities. It could also be partial pressure of oxygen, the ambient pressure and so on and so forth. So, this defect concentration may be independent of temperature in certain cases, right, or at least there is a certain window when this is independent. So, basically, and generally what happens is that there is a crossover. So, there is a point at which transition occurs from intrinsic to extrinsic or extrinsic to intrinsic, depending upon how you look at it, at which transition happens. So, basically you say that intrinsic to extrinsic, and this could be, for example, temperature. Okay, the temperature at which a solid will show behavior like intrinsic, and below a certain temperature it will show extrinsic behavior. So, for example, if we take case of, let us say we take a case of two oxides. Okay. So, let us say we take a case of MgO. MgO has Schottky defect formation energy of 7.7 electron volt. On the other hand, if you look at the case of NaCl, so this is MgO. If you look at NaCl, then delta Hs is approximately 2.4 electron volt. So, as a result, the melting point of MgO is about 2850 degrees centigrade approximately, and for the sodium chloride it is about 800 degrees centigrade. Okay. Now, you can see that we saw that n by n is equal to exponential of minus delta H, in this case we can write Hs divided by 2 kT. So, at any given temperature above 0 Kelvin, the defect concentration in NaCl will be larger than defect in MgO. Okay. But so NaCl, because of its lower melting point and lower defect formation energy, will have more number of defects. However, in case of MgO, so these oxides are all prone to having certain impurities. So, let us say we can put certain impurities in MgO, and that MgO impurity level is 1 ppm, whereas in case of sodium chloride the impurity level is 50 ppm. And generally these impurities are basically aliovalent. Aliovalent means different valence cations. Okay. Aliovalence means not isovalent. So, both of these are M2 plus. So, it could be MF plus or MF 3 plus. Okay. For MgO. Okay. And for NaCl it could be Mf2 plus or Mf3 plus, because Na is 2 plus. So, now let us see. So, as a result the concentration, the extrinsic defects is much higher than the defect. So, in case of MgO, when we put in 1 ppm of, let us say, Al2O3, okay. So, when you put in 1 ppm of Al2O3, what will you create? So, Al2O3 will go to MgO. So, here both the aluminum atoms go to oxygen site, magnesium site. All the 3 oxygens will go to oxygen site, let us say, and then we create, let us say, vacancy of magnesium. So, this will be positively charged, this will be negatively charged. So, we create this vacancy of magnesium. So, for every ppm of, so you can see that 1 mole of Al2O3 creates 1 mole of oxygen vacancies. Okay. So, if you have 1 ppm of Al2O3 present, which means that you will have 1 ppm of vacancies, and this 1 ppm is a very large number, it is 10 to the power minus 6. So, basically we are saying n to the power n is equal to 10 to the power minus 6. So, when you plot this as a function of temperature, so when you plot the impurity concentration as a function of, so we will have to plot in this fashion. So, let us say this is log of n. So, for an intrinsic solid, we see that there is a exponential relationship. So, as you increase the temperature, the concentration will increase, and this is in the exponential manner. This is for intrinsic MgO, and the energy will be given by this slope. So, this gives me delta Hs of approximately 7.7 eV. Now, at very low temperature, this concentration will be extremely low. It will be minus 15, minus 16, 10 to the minus 15, 10 to the minus 16, 10 to the minus 10. Now that I have put in a impurity of minus 6 concentration, I can draw a line of minus 6 concentration at certain point. So, this corresponds to 10 to the minus 6. So, which means up to this temperature, no matter what the temperature is, the impurity, the vacancy concentration will always be 10 to the power minus 6. Okay. The intrinsic vacancy concentration is very low as compared to extrinsic vacancy concentration. So, this region will become what we call as extrinsic region. It is only at this point the intrinsic concentration takes over the extrinsic concentration, and then we reach in a regime which is called as intrinsic regime. So, basically if you want to plot now the final concentration plot, the final concentration plot would be something like this. It would be like this, and then it follows for a impure MgO. So, up to a certain temperature, let us say T1. So, as you increase the temperature from this side, up to a certain temperature, the concentration of vacancy remains constant at 1 ppm. It is only after T1 when impurity concentration, the intrinsic vacancy concentration increases, then it becomes intrinsic. And this is also manifested in conductivity. The conductivity in these systems is also proportional to the concentration of vacancies. So, the conductivity, if you plot conductivity here, we have not seen the expression of conductivity, but conductivity will also show similar behavior. The conductivity will show behavior like this up to this point, and then conductivity will show a constant value up to this point. This is true for sodium chloride, it is also true for silicon, it is also true for many doped systems in which there is an extrinsic region, there is an intrinsic region, and extrinsic to intrinsic region crossover happens at a particular temperature when intrinsic defects start increasing in number exponentially and they take over the extrinsic defect concentration. Okay. So, this is also a way of controlling the carrier concentration. So, when you dope something with something else, then you can create sufficient number of carriers in them so that the solid becomes conducting up to a certain temperature and determined by the impurity concentration primarily. So, within this region, this constant behavior is basically the extrinsic behavior. There is this constancy of concentration as well as the properties. So, this is what I wanted to convey. So, even though sodium chloride, even though magnesium oxide has lower number of defects, if you put in impurities in that, it can become conducting by putting sufficient number of impurities. So, now let us move to different defect equilibrium in these oxides. So, we move to defect equilibrium, and this defect equilibrium basically first we will take example of stoichiometric. So, basically what will be the equilibrium concentration of defects under given set of conditions, that is what is defect equilibrium. So, in this case we consider first Schottky defects. So, we first look at Schottky defects. So, let us say the oxide is MO, so the binary oxide. So, how do you write the defect reaction? The defect reaction is basically 0. So, this will be, so Schottky defect will have vacancy of metal plus vacancy of oxygen. This is negatively charged, this is positively charged. So, we can write a equilibrium constant. So, equilibrium reaction constant for this, let us say this is 1, for 1 would be Ks is equal to VO multiplied by V. So, Vm multiplied by Vo. We could have written in terms of activity, but let us say it is 100% activity kind of system. So, basically square brackets denote concentration, right. The brackets, all right. So, the equilibrium constant, but equilibrium constant for a given reaction can also be expressed as, we can write delta Gs for this reaction as minus of RT ln Ks, okay, the change in so when we say free energy, by definition it means gives free energy in these systems. So, we can write this Ks as exponential of minus of delta Gs divided by, you can write RT or KT, but let us say we write in terms of RT. So, here delta Gs is basically the molar free energy of defect formation, and basically this will be equal to delta Hs minus T delta Ss. So, this is, you can say this is molar free energy, okay, and delta Hs would be the enthalpy of defect formation, and delta Ss would be the change in the entropy, which is mainly vibrational in nature, and we ignore that for most cases. So, we can approximate this as del Ks to be equal to, so if let us say this is negligible, basically it is vibrational in nature, then we can approximate this as minus of delta Hs divided by RT, okay, RT or KT depending upon the unit you can write. So, if Schottky defects were to dominate, then we can write, so now from this equation you can write, now in case of Schottky defects, in case of Schottky defects, we know that delta, Vm is equal to Vo, because for MO, but if it is not for MO, if it is for M2O3, then it would be different. What would it be? V for M2O3, for M2O3 you will have 2 Vm and 3 Vo, which means for every 2 metal vacancies you are forming 3 oxygen vacancies, which means Vo will be equal to 3/2 Vm. This is for M2O3. So, accordingly the defect constant will change, the reaction constant will change. So, if this is true for MO, we are taking for MO, then for MO I can write Vm dash double dash is equal to Vo double dash, which is equal to Ks to the power Ks to the power half, right? Is that's right, because we say that Ks is equal to product of these two. So, when you put in substitute one of them, then it becomes Ks to the power half. So, then you can write this as basically Vo is equal to Vm, which is equal to Ks to the power half, and what was Ks? Ks was exponential of minus delta Hf divided by Kt or Rt to the power half. So, this becomes exponential of minus delta Hf divided by 2 Rt. So, this is what we got from thermodynamics as well when we calculated the concentration, right. So, this is delta Hf divided by 2 Kt. So, we can see in this case that Vm and Vo are dependent only on dependence of defects only on temperature. Despite being an oxide, it does not depend upon partial pressure of oxygen. There is no partial pressure of oxygen that is playing a role here. So, you can do the same, so you can do as an exercise, do similar exercise for Frankel defects as well as Schottky for, you can say, M2O3, what will happen for M2O3, what will happen for M2O, what will happen for M2O5, and so on and so forth. Okay. So, this is homework exercise for. Okay. So, this is fairly straightforward. You can see and you will see the same thing in case of Frankel defects as well, that defect concentration will remain independent of partial pressure of oxygen. It will depend only upon temperature. Next thing that we see is defect equilibria and in non-stoichiometric solids. So, this is about the stoichiometric oxides. So, this we have taken for Schottky defect, and you can do the same exercise for. So, B can be for Frankel defects. This is basically your homework, okay. And the answer in that case would be, let me give you the hint, you will get Mi will be equal to Vm, this will be equal to some constant K naught. So, you can also write these in. So, if you take Ks to be Gs in the form of Gs, then sometimes what people do is that everything which is constant comes out as K naught. So, this will become K naught to the power half, but even if you do not write K naught, you should understand the expression. So, this could be it's basically you can say K naught, some K naught, some constant to the power half into exponential of minus of delta Hf divided by 2 Rt. You should get similar expression for Frankel. Okay. Now, let us move on to the next thing, which is defect equilibria in non-stoichiometric okay. So, let us take the first case of let us say oxygen deficient oxides. So, which means we consider case of MO, let us say. So, what are the possibilities? The possibilities are when oxygen vacancy dominates, so what kind of defects will be present will depend upon the defect formation energy. So, whichever defect, see, when you form the defect, then defects are formed in a lattice, and every lattice has certain energy with respect to formation of defects. So, very close packed lattice, generally putting in interstitials is more difficult as compared to creating vacancies, because for putting in something you need to expand and dilate the lattice, whereas creating vacancies is just removing an atom. So, especially anion vacancies are far more difficult because anions are bigger. On the other hand, cation vacancies are easier to form. So, it depends upon the defect formation energy what defects will dominate. So, there could be multiple scenarios. The first scenario is when oxygen vacancies dominate. So, if you have oxygen vacancies, you can also have metal interstitial, not mental, it should be metal. And third scenario could be mixed, when both are present. So, these are the three scenarios that we will look at, that we take the case of defect non-equilibrium will mean, non-stoichiometric will mean you will have either MO1 minus delta, or you will have MO1 plus delta O, or you can have M1 minus delta O, or you can have MO1 plus delta. These are the non-stoichiometric cases. So, these are the three cases that we will see. We first take the case of oxygen deficient oxides in case of MO most likely in most cases, and then first case is when oxygen vacancy dominates, the second case is when metal interstitials dominate, and third case is when both of them could be present both of them could be simultaneously present. So, we will do the analysis of this in the next class, and we will stop here today. So, what we have done is we have basically today looked at we have moved beyond the impurity concentration. We also looked at how when you put in impurity you can tailor the concentrations and giving rise to two regions, one is extrinsic, second is intrinsic, and generally you will see, for example, phosphorus and silicon and even some other higher impurity oxide and lower impurity in a pure oxide will give rise to extrinsic region at lower temperature, which is dominated by presence of appropriate defect, which could be vacancy or interstitial, followed by at high temperature intrinsic region when intrinsic defect concentration takes over the extrinsic concentration. So, we will stop here today. We will do this, we will expand upon this defect equilibrium non-stoichiometric oxides in the next lecture. Thank you.